This video is a really quick run through of the rate equations topic in AQA A-level chemistry, including the dreaded Arrhenius equation. This is a speedrun summary video, so I've explained things really quickly and there aren't practice questions. If you do need more detail because you're learning this topic for the first time or you want to go over it in some depth, there are currently 12 videos in my full kinetics and rate equations playlist, so have a little look at those. The rate of reaction is the speed with which the concentration of either a product or a reactant is changing, and we show it using square brackets. Rate is measured in moles per decimeter cubed per second because concentration is measured in moles per decimeter cubed and change in time is measured in seconds. Rates of reaction are governed by collision theory, which is the idea that in order to react, particles need to collide and they need to have the activation energy. Changing concentration is one of the 5 ways to alter the rate of reaction. At GCSE, you showed that as you double the concentration of hydrochloric acid, you halve the amount of time for a cross to disappear in the reaction with sodium thiosulfate. But this is not the same for every reactant in every reaction. If a reactant is in excess, it doesn't matter if you increase the concentration because you've already got too much of it. In addition, multi-step reactions may have one single rate-determining step, and reactants involved in the other steps may not affect the rate. You're not expected to know examples of reactants that do and don't affect the rate, but you do need to be able to show using data what the impact of change in concentration will be. For any reaction, we can work out something called the order of that reaction, and this is the sum of all the partial orders of all the reactants in that reaction. This gives information about how the rate of reaction can be controlled, and it's determined by experimental data, not just by looking at the equation for that reaction. For the purposes of A-level, you have 3 options, so determining partial order is really a multiple choice question. If the partial order of a reaction with respect to reactant A is 0, which is often the case for enzyme catalyzed reactions, and is also going to be the case if that reactant isn't part of the slower step, then if I double the concentration of A, there will be no effect on the rate at all. A partial order of 1 means that if I double the concentration, the rate doubles, and a partial order of 2 shows a squared relationship. So if I double the concentration of A, my rate will quadruple, and if I triple the concentration of A, my rate will increase by a factor of 9. You should be able to determine order both graphically and numerically. These are the graphs that you should recognise for a 0-order reaction, a 1st-order reaction, and a 2nd-order reaction. These data are derived from looking at changes in concentration over time. In order to turn these graphs into the graphs we just saw, we need to draw tangents in order to work out what the gradient is. So you can see that for the 0-order graph, as the reaction progresses, the reaction doesn't speed up or slow down, so the gradient doesn't change. Whereas for the 1st order, it slows down, and for the 2nd order, it slows down more dramatically. These graphs are concentration time graphs, and they're going to be for a reactant because the concentration is decreasing. They tell us how the concentration is changing over the time. So in order to work out what the gradient at a particular point is, we need to draw tangents like this. Typically, an exam question will provide you with a data table and ask you to identify the partial order or deduce the overall rate equation. Firstly, look for a pair of experiments where the concentration of only one reactant has changed. Here, experiment 1 and 2 have the same concentration of B and only A has changed. By looking at A, I can deduce the partial order with respect to A. The initial concentration of A has increased from 0.12 to 0.36, so it's tripled. The reaction must be 0, 1st or 2nd order with respect to A, so the rate must either not change, or triple, or increase by a factor of 9. So if I look at this, I can see that it has increased by a factor of 9, and therefore it is 2nd order with respect to A. I now need to work out what the partial order with respect to B is, but in order to do that I need a pair of experiments where B changes and nothing else does, and I don't have this set of experiments. So what I need to do is predict the outcome of a hypothetical 4th experiment to allow me to partition up the change in rate caused by A and the change caused by B. So I'm going to make up a hypothetical 4th experiment, and in this I'm going to change A as we see in experiment 3, because I already know what change in the rate that should cause. But I'm going to keep B the same as it was in experiment 2. And the reason that I'm doing that is it allows me to work out what would happen if only A had changed, which will be what would happen if we were 0 order with respect to B. So I'm going to compare those two and say this doubles, so this should times by 4 because I already know that we are 2nd order with respect to A. And that gives me a value of the rate that I can then go back and compare to experiment 3. So now I can look at 4 and 3 together, and A is going to be the same, but B is changing. So I can see that the concentration of B has halved, and therefore my options are that the rate is the same between 3 and 4, that the rate has also halved, or that the rate has quartered. And looking at this, it has halved, and therefore this reaction is first order with respect to B. This question asked me to deduce the rate equation, so it's not enough to just know what the partial orders are, I need to put them in the right format. So this is always going to take the form rate equals K, which is the rate constant that we'll talk about in a second, and then square brackets around each of the reactants that the partial order is more than 0, and then you use the partial order as the power. Now about K. For any chemical reaction, we can say that the overall rate is going to be proportional to the concentration of each one of the reactants to the power of whatever its partial order is. Be aware that these partial orders have nothing to do with the coefficients in the chemical symbol equation, they are derived experimentally. While it's useful conceptually to say that rate is proportional to the concentrations of A and B, if I actually want to make some predictions, I need to know what the value of that proportionality is. So we replace that alpha fish sign with an equals and a K, and the K is the rate constant, which is going to give us an actual mathematical numerical relationship between those concentrations and the overall rate. So for any given reaction, rate is going to be equal to a constant that I can work out experimentally, multiplied by the concentration of each one of those reactants raised to the power of the relevant order. Like Kc and Kp, which is coming up in a second, K will have different units for different reactions. Rate is measured in moles per decimeter cubed per second, and concentration is measured in moles per decimeter cubed. That means that if your rate equation only contains one concentration term, then your units for K will be seconds to the -1, and then if it contains two terms, it will be moles to the -1 decimeters cubed, seconds to the -1, and so on and so forth. Not every step in a multi-step reaction will go as quickly as the others, so the overall rate is determined by the rate determining step, which is the slowest step. It isn't the first step, and you can't work it out just by looking at the chemical symbol equation. We need this experimental data, and we need to know what our rate equation is. What we do know is that the reactants in the rate determining step will feature in the rate equation, so they're not 0th order. If I look at my rate equation, I can see that it features both A and B, and it doesn't include C. So C cannot be involved in the rate determining step, and therefore the rate determining step cannot be step 2, it must be step 1. But also note that A is second order, so therefore I need to include 2 moles of A in my rate determining step, which I do have here. If I just look at this rate equation, I can immediately say that the rate determining step for this reaction must include 1 mole of E reacting with 2 moles of F. Sometimes this might be slightly more ambiguous and you might need to think about it a little bit. So here you can see that in my rate equation I've got G being second order and H being first order, but none of the steps that I've got listed below include 2 moles of G and 1 mole of H. So what I need to remember is that those 2 moles of G have made up I, and then I has reacted with H. So in order to get to the end of step 2, I've needed to use 2 moles of G and a mole of H. So step 2 here is going to be my rate determining step. We know that we can use this rate equation to characterise the rate of reaction, and this includes the concentration data. But as we know, concentration being changed is not the only way to influence the rate of reaction. As you increase the temperature of a reaction, this also increases the rate, and we can relate this to the frequency of collisions and also to the number of particles that have the activation energy. But if increasing temperature increases the rate while not affecting concentration, then temperature must be linked to K. The Arrhenius equation allows us to say quantitatively what will happen to the rate of reaction as temperature changes. It's an equation that describes the relationship between activation energy, temperature and rate, and this allows us to make predictions not just about changing the temperature, but also what would happen if we introduced a catalyst and therefore altered the activation energy. K is that rate constant that we've just been calculating, and it doesn't have specific units, you need to work them out for that particular reaction. T is the temperature in Kelvin, R is the gas constant in joules per mole per Kelvin, EA is the activation energy, and into this equation you need to put it in joules per mole, but it's usually given in kilojoules per mole, or that's the units that you're asked to write it in if that's what you're working out from a question. And then E is an irrational number with a value of about 2.72, and your scientific calculator should have a button for E. And A is our Arrhenius constant, which is a pre-exponential factor, and it's the number for that particular reaction that relates to the collision frequency and also the orientation of the particles. The Arrhenius constant, again, doesn't have specific units that are never changed, and it will have the same units as K for that particular reaction. The other thing that you need to watch out for is that at the back end we have that whole massive index term. So I would work that out separately. So you're going to take activation energy divided by the gas constant and the temperature, and all of that as a negative power just applies to E. It doesn't apply to the A Arrhenius constant term. This question is about as simple as it can get because it's just a clean substitution. So I'm going to start off by writing down my Arrhenius equation, which I need to have memorised, and then personally my preference is always to work out the value of that power separately. So I'm going to do that, bearing in mind that the activation energy needs to be in joules per mole, and of course the temperature needs to be in Kelvin, and that gives me a value for that power. So I can then substitute that into that equation to give me an answer, which I'm going to leave to a sensible number of significant figures. Here I've done it to 3 because that's the number in the question. And then remember, my units for K will be the same as my units for A. So here it's going to be seconds to the -1. Working out the activation energy for a particular reaction is a really common A-level question. So we do need to be able to rearrange the Arrhenius equation to make every single one of the values the subject. So I would really recommend that you memorise both the original Arrhenius question and one rearranged form that contains the logs, because trying to shift between non-logarithmic numbers and logarithmic numbers under pressure is really quite challenging. So here we've got a slightly more challenging example where we're having to calculate the activation energy. As we've said, the equation is going to spit out the number in joules per mole, and we will need to convert it at the end. So I'm going to give my rearranged version of the Arrhenius equation. I'm going to work out this, and I'm going to need to convert the temperature, but also I'm going to need to take the natural log of my values of A and K. And then when I substitute all those numbers in, I get a nice big number for my activation energy, which I then need to convert to kilojoules per mole, and again round to an appropriate number of significant figures. We can also determine the activation energy graphically by comparing the natural log of K to 1 over the temperature. So natural log of K is your y-axis and 1 over the temperature is the x-axis. And if we think about the equation for the natural log of K, and we do a little bit of rearranging to get it into the form y equals mx plus c, then we're going to get ln K is minus the activation energy over RT plus ln A. And remember that 1 over T is our value for x. So therefore our gradient is minus activation energy over R, the gas constant, and our intercept is going to be the natural log of the Arrhenius constant. Typically you will need to process this data before you can graph it. So that will involve converting temperatures to Kelvin, working out the reciprocal of those temperatures, and also taking the natural log of K. And these are going to be negative numbers here because our value for K is less than 1. So because of this, we're expecting a graph that actually is going down below the x-axis and looks a little bit like this. As we've said, the gradient is going to be negative activation energy over R. So you need to make your line into a triangle and work out what your change in y and your change in x are. And that will give you a value for your gradient. Then if you divide that by -1 and multiply it by the gas constant, you get a value for the activation energy, which of course you then need to convert into kilojoules per mole. It is possible to calculate a value for the Arrhenius constant graphically, but it's much more likely that you'll calculate the activation energy graphically and then go back to numerical calculations for A. So we know that the natural log of A is the natural log of K plus the activation energy divided by RT. And so we can go back to the data that we have in the data table and the value of the activation energy that you just calculated. By substituting in the value of the gas constant and the temperature, we get a value for RT, and then we can do the activation energy that we just calculated divided by that RT, and then we will be able to work out a value for the natural log of A. And then to kind of undo that natural log, we need to do e to the power of that number that we've got there, which gives us the value of a being 2.79 times 10 to the 5, and the units, remember, will be the same as the units that we were given for k. Thank you very much for watching, and I hope that you found that a useful, albeit speedy, recap of the rate equations topic. If you do want some more practice, particularly of those Arrhenius questions, there are a number of full-length videos which go into more detail and also have more practice questions.